So hello, this is the makeup lecture for the ELE 481/ELE 522 undergrad grad lecture for power fundamentals. Before we do that, the first thing I want to go over is to show you how to actually run Putty off your laptop when you are not in the on campus on the machines. So the first thing you want to do is we're going to do a virtual private network, or VPN. So you're going to want to go to vpn.olemiss.edu, and this will bring up a login page. So it has a number of options: faculty, staff, or local. You should be able to log in with local. If you're not able to do this, let me know and I'll contact IT. So it's going to let you log in, and then it will try to detect a number of different applets to click allow here. Allow and remember. And so this should allow you to do all the cadence stuff. But once either it's going to tell you can download everything, or I'm not going to go through all that. One thing it'll allow you to do, though, is once you download, sometimes it might say you don't have everything, but what you can type in is you can type in Cisco. It'll download a file. So if we'll say stop plugin, it won't work. But if you type in Cisco and it works, you type in Anyconnect, and here it'll bring up this Cisco Anyconnect Secure Mobility Client. You type in vpn.olemiss.edu. Now I'm already connected, but if you click connect, you will be able to log in. You use the local, and then type in your password. And so that will allow it to work. So the next thing you need to do is you need to download a few programs. But they don't take very long to install. You go away. So let's open up. First thing you want to do is you want to search for Putty. So Putty is an SSH client, as you know. So putty.org. Third link is download Putty. So this depends on if you're trying to use it on Linux, you can download it using a tar.gz file or an MSI for Windows installer. You also can just straight up download the 32-bit putty.exe. So that's what I have downloaded here. The next thing you need to do is you need to download a program called Xming. So you Google Xming, and it's an X server. So this will allow you to actually run the graphical user interfaces on your machine. So you can click here, and you can download this file. So you download that file here, you run everything, and it will work. The next thing you need to do is you need to get something called Ming Fonts. So you go back here, and you click on this. Click on 7 points, and then you bring in your Ming Font setup. This will allow you to actually render specific fonts that Cadence uses in order to actually be able to see what it is that Cadence is trying to render. So you click on that, you download it, you run the executable. And then last thing, you can download FileZilla. It's also free. And then you download client. You're not running a server on your machine. You could download the client, and then you can run everything from your machine. So if once you actually start running it, you have the VPN running. First thing you do is you click on Xming. Doesn't do anything, but it is running in the background. Now you bring up Putty. You log into the Cadence server. And allow you to log in. So now we have proven that the VPN has worked. So you're able to log in, and there you go. So one other trick I wanted to show you, since especially for the undergrads, you're working in groups. I have an account here. I have everything, so I got Verilog and Virtuoso on this machine. I've been running a separate account, Rebel VLSI, to run all the demos, as you've seen on the lab. So this is particularly useful if for some reason you realize that you have a specific file on your partner's machine. So I can SSH into that account, and then I can use the different password here. And now I'm in Rebel VLSI. So now there I can actually see I hired Block, Innovis, all these different programs. So what you end up doing is then you can exit, and then you can remove the connection from Rebel VLSI. Now I'm back in the other account. Here I can press exit again, and then it closes out the program. So now hopefully this will work this time. So what we're going to do is we are going to learn about power. So what is power? So we define it formally as the work done on charge carriers between a potential difference in a circuit over a given time. The SI unit, power, is the watt and the joule per second. Power is drawn from a voltage source attached to VDD pins on a chip. So this kind of makes sense. So now we know how supply voltages work. We also know that P equals IV, PV equals, so you have voltage equals IR, so you're going to I squared R or V squared over R for your power generation. And this becomes important because we want to use this power equation to relate to energy. So energy is the rate of power consumption. So if you have some sort of, let's say, your voltage time. So once the voltage goes from 0 to 1, you have some sort of change. We're going to be learning that there's going to be a spike in power consumption at kind of a lower level of power consumption. But the overwhelming majority of power consumption is going to happen here during dynamic power consumption, during the changes. So it's probably going to look more like this for power, because it'll go during this and then after it will spike down. So while it's holding the power consumption, it's static power. So we can actually measure the energy as the integral, or the area under the curve here, or area under the waveform. And the average power is that energy divided by time. So energy is the rate of power consumption, and is found using the equation E equals the integral from 0 to t p dt. And the average power of the circuit is the energy consumed by a circuit over a given period of time. So it's just that equation from 2.2 divided by t. So now we're trying to actually relate these to how this works in a circuit. So remember, in a voltage source, you have your current running through, so P equals I of t, V of t. And then you have a resistor, so you have the voltage across the resistor given at any given moment, squared over T is equal to I squared R. So what is the energy stored in a capacitor? So this becomes important because a lot of the output capacitances, and we're going to learn this as we get more into how a transistor works, but there's a lot of capacitances between plates. So we now know how a transistor is laid out. So you have your diffusion regions, you have your silicon, you have your gate, you have your, so you got N minus, right? So you're trying to create a P plus channel here. So you have two different doped type materials here, two different doped materials here. Here, here as well, you have all kinds of different, you have all these different capacitances. And this is just the difference between two plates. So this becomes very important when trying to study all these different factors that work in how a capacitor works. I mean, that's how a transistor works. So we're going to go through this equation here. So we already know this. So from 0 to infinity, So recall that you learned this in electronics and electric circuits, that I equals C of dV dt. So you have some sort of function of the voltage. And so you plug it into, going back to calculus 1, you plug in I of t here, C dV dt. So these are going to cancel out. So what you're going to see is this, you bring out the capacitance, it's a constant. So the voltage goes from 0 to V of C of V of t dV. So this becomes capacitance times the voltage on the capacitance over 2. So why is this important? So when the gate output rises, the energy stored capacitor is 1/2 CLVD dt. So we have this load capacitance on the output, and this is what ends up happening is now you're putting two transistors together, as I showed you in that layout before, right? So you have this. Well, guess what? You have some sort of distance here. Now you've got your load capacitance. So now the energy drawn from the supply, okay, so you got this voltage here. Do the same thing here. We'll put in our equations. Now this VDD, it's always going to be VDD, right? So now you have CL VDD times the integral of 0 to VDD of dV dt. Well, guess what? When you do this, it just becomes V, which is also VDD. So now you get CL VDD squared. That means that half the energy from the supply is going to be dissipated in the PMOS transistor in heat, and the other half is going to be stored in the capacitor. And so then when the gate falls, well, that supply voltage is ground, but what's going to happen is that the energy in the capacitor is going to be dumped to ground. So you have this output capacitance, and then when you have the flow going from 0 to 0, well, now it's going to dissipate. And that energy is dumped to the ground. It's dissipated as heat, right? So this is where, when you feel the bottom of your laptop, and that's heat, that's what's going on there. You have this energy that's being dissipated by zeros falling down. So I talked about this difference between static and dynamic power consumption. So static power consumption occurs when the circuit is not charging voltage, or not changing voltage. So it's just, we have a full waveform here, right? Static power consumption occurs here, here, here. So we have the sub-threshold leakage plus the gate leakage. So you have all these leakages that are occurring between the different the diffusion regions and the biases and the bases and the SiO2s and the gates, and then junction leakage. So this is just a fundamental equation here. But dynamic power consumption occurs when the circuit inputs switch. So here and here. And so that's your switching load capacitances and your short circuit current. So short circuit current is the current in a CMOS circuit during the brief instance when both the PMOS and the NMOS transistors are on simultaneously. So this would be one of those things where we go into much more detail in CMOS as opposed to low power VLSI design. But what ends up happening is you're going to have in a pull-up, pull-down network the same voltages both on PMOS and NMOS. So what's going to happen is, when there's going to be a brief moment when both of these transistors are on, very brief. So we would go into a lot of detail here about this, what stage they're on, where you have your PMOS, then you're going to have switching regions, and then fully on here. The key detail for what you need to know is that there's power consumption going on specifically when it's switching. And so what we're going to do is we're actually calculate here, and this is an important equation. I highly recommend you know this. You'll see this over and over again when you're coming up with different methods for synthesis. So you have 1 over T, so you have this energy equation that we've come up with, right? We know that we have our supply voltage from our current from the supply. We also know that we have the switching frequency, right? So what's going to end up happening is that we know that time is constant, and we know the supply voltage is constant, so we can bring that out here. So this is going to become ID dt d of t, as you can see here. So what's going to end up happening? So this is dependent upon the switching frequency. If you recall, it's C. You got the coefficients of di dt, right? dv dt. So if we go all the way back up here, sorry, I meant dv dt. So using that knowledge, we can actually figure out that CV dv, and then times the frequency times the time, times the whole time that we do this. So how many switches occur over this time period? So what ends up happening is that these cancel out, and the result is that the the power consumption is equal to C. You'll typically see this as CLVDD squared times the frequency. So this is important because this means that frequency is directly proportional to power consumption. What ends up happening is that we're trying to get this down. So typically, the easiest way to get that is to have that go down. The problem is people don't like this. People want their computers running fast. People want their phones running fast. People want their chargers running fast. And if you're not conscious about how low power VLSI design works, what ends up happening is that you have a scenario where you get your Galaxy Note 7, because they didn't properly account for all of the switching between caches and monitoring the battery. They're focused so much on performance, which, by the way, if you're not a professional, and you're just using your phone and your phone starts running slow, you get frustrated, right? You're not thinking, okay, well, it's running slow, but thank goodness they're doing everything to make sure that it doesn't blow up in my hand, right? No, you're just more concerned about running your Pokemon Go or whatever new fad is out today that will make me feel older and older every day. So next I want to briefly talk about this activity factor. So computers don't always, the clock will always switch consistently, but that doesn't necessarily mean that the output will. AND gates, for example, got 0, 0, 0, 1, 1, 0, and then 1, 1, right? Very simple. Well, it's only going to have one switch over 4 cycles. So eventually it's going to come back down here. So the activity factor is the probability that the circuit node transitions from 0 to 1. And then what ends up happening is, based on that, we can use this activity factor to determine the switching power. So since an inverter, the probability is 0.5, this becomes 1/2 CLVDD squared over frequency. So for an AND gate, it's 1/4. See what I'm saying? So that's one way reducing power consumption, is figuring out how to produce your logic with the minimum number of switches. So, and then I include a note here that if you multiply the power times the to get energy, you just multiply the frequency times the time, and then you're going to get for your CLVDD, and then you multiply the frequency times the time, And that's how you get that. So next, I want to go over some fundamental concepts on clock gating. How much time have we used? 20? Okay. Basically, there's a lot of ways to try to reduce power. The main idea is that we're going to focus on how to reduce power by turning certain portions of the circuit off or limiting the amount of power that's used, particularly in memory elements. And first one we're going to talk about is this concept called clock gating. So clock gating, we're going to take a signal that ANDs the clock signal and an enable signal to turn off the clock idle. Clock gating ANDs a clock signal and an enable signal to turn off the clock to idle blocks. So what we're trying to do is we're trying to reduce our switching activity by saying, okay, well, we're going to reduce the probability that it'll switch by turning it off completely when we're not using it. And so it saves all this, eliminates the switching activity in the block. And the drawback is it requires determining if the block will be used. Well, if we're going to determine the block's going to be used, what ends up happening is that we actually have to build more circuitry into the circuit. So this is another trade-off that you have to be conscious of as we get into low power design. In order to get around the fact that power and frequency are proportional, we have to be very conscious of that you add circuitry to reduce power consumption in other areas. So oftentimes low power ends up coming with a bigger circuit and a potentially higher cost and lower performance. But there are, as we saw at the beginning of the course, low power is becoming more and more important. So as the transistor sizes get smaller and smaller and we have larger circuits, what's going to end up happening is that we need to be very conscious of how these impact everything. So in this case, what's going to happen here with clock gating is we have some sort of enable logic that we had to design to determine whether or not the circuit's going to work. This means that we have these registers and we have all these other elements down here that are saying, okay, based on if this is enabled, we're going to run this circuit. So when it happens, we have an enable latch and a clock. So when it's 0, it turns on and passes everything through. And then the clock changes to 1, and now the value of the enable latch, when AND gate input is 1, the output is just equal to this input. So what ends up happening is this input gets then sent to these registers. So that's on only when the enable logic is enabled, and once the clock, so you know how latches work, so this is going to be 0, so we're going to put it on the latch, and then once the clock moves, it won't allow anything on the previous enable logic in. So once the clock goes to 0, 1, you put the output on the gate here, it'll run, clock gate will work fine. Meanwhile, everything in the updating of the enable logic will not pass through until the next clock cycle. So here's some other fundamental ways of reducing power via capacitance. So we also know that we have our power equals load capacitance times the supply voltage squared times the frequency. So one thing you probably are thinking is right here, supply voltage. As the supply voltage goes down, the minimum required voltage put on the gate in order to produce a switch, it's your threshold voltage. That's going to go down in instances where the gates get smaller and smaller. So it used to, supply voltages used to be 5 volts. Now they're down to about 1 volt or 0.9 volts. So that means if you have a reduction of 5 to 1 here, what's going to end up happening is you're reducing power consumption by a factor of 25. But as we learned in the previous section that the trade-offs between smaller devices, smaller transistors, ends up causing a bunch of other issues. But that's why we're engineers. We try to come up with the methods to solve them. So you have gate capacitance. So fewer stages of logic. That's where your Quine-Mikulski from 235 comes into play. Your K-maps, all these different logic reduction algorithms. Anything you can do to actually reduce the amount of logic that you need to do to execute your design will be done that way. And also smaller gate sizes. So in this instance, if you recall, I mentioned that, for example, so you have an AND gate, or a NAND gate here, right? This is going to be output, and then we have our A and B inputs, right? So these circuits are going to be smaller than AND gates. And even more importantly, and we'll learn this more, these NOR actually requires larger sizes than NAND. So that's why a lot of the logic synthesis you're going to see, if you can reduce everything to NAND gates, you're in really good shape. Because that's going to be smaller gate sizes, and then you typically do it with fewer stages of logic. So another thing we can talk about is wire capacitance. So wire capacitance, we're going to be learning a lot, not in the next section, but the section after, about floor planning. So basically the idea of floor planning is we have what's known as a pad frame. So you have all these pads around the output, and we're going to be putting in values. So you got supply voltage, you got your A input, ground, however it ends up getting laid out. And a good example, if you have these smart cards that you have on your chips, on your credit cards now, you have, if you look at it, you have these little these are all different pins. So when it pins in, it runs. So, and you see a lot of people, they'll complain about how long the chip cards take. Well, that's a bunch of added security to ensure that your chips don't get, your information doesn't get stolen. That's another example of when the customer doesn't necessarily understand or care about high performance versus security versus low power. But if you have long drivers with inverters or buffers rather than complex gates, this becomes an issue. And so something I wanted to bring up here, I don't actually have, I kind of assume that you all know what Kogi stone is. So it's and so you all are familiar with fundamental adders. So if you haven't, I can just go to images. And so what ends up happening is you have these propagate and generate logic, and at these different levels. The key thing for this particular lecture, and any of these will do, is you can see how you have these really long wires, right? And so you're trying to do 8-bit. If you're trying to do 64-bit, these wires are going to go on for a long time. Now the benefit of a Kogi stone adder is that it runs fast. But as you can see here, in the instance where these long wires aren't mitigated, you get a lot of energy here. Right? So here you're doing 63 bits, you have 63-bit slices, and this just gets larger and larger, and it causes more problems. So delay is minimized, but in order to reduce this delay, we have these long wires that have to go to all these different stages. And so what's going to end up happening is, if we have a circuit where there's 10% higher delay, but the smaller gate sizes result in driving wires with inverters and buffers instead, well, look what happens. Significant reduction in both energy and power consumption. So what ends up happening is they reduce by increasing delay with smaller gate sizes in all of these different stages. What they were able to do is consume less power. It just took a little extra time. So it takes 10% longer, but obtains a 55% reduction in power consumption. So voltage and frequency. So as we saw before, voltage is a quadratic effect in dynamic power. So we saw that equals CL VDD squared times the frequency. So that's our quadratic equation here. So as I alluded to a little bit ago, we do know that reducing power consumption through the supply voltage is problematic because we require certain threshold voltages in order to make the switch occur in the transistor to mitigate non-ideal transistor effects. So what ends up going to happen is we have to calculate what the lowest possible voltage for each block is that meets the performance requirements. So let's say this one runs at, let's say the supply voltage is 5 volts. And we figure out that we can run this at 4.1, and we can run this at, this one needs to be run at 5, and this one needs to be run at 3.8. Well, instead of running this at 5 and 5 and 5, especially if we don't have to worry about performance at the 5. So what this means is that if we can, you have 5, you're going to get a much stronger signal through your transistors. 4.1 is you're going to meet your noise margin areas. So it's still going to work. It's just not going to work as well. So here I give an example of when you want to do something. So we have this battery in our laptops, and when you're plugged in, like I'm plugged in right now, it's going to run a very high performance because you don't have to worry about limited power. I'm just getting it from the plug. But the moment I unplug everything, you're going to notice that I've now switched. So now it's going to run on different power consumption. It's going to have different approaches to it, particularly with screen brightness, what type of programs can run in the background, how fast they're running. All of this is going to change quite a bit. So let's see. I tend to go pretty fast on these videos. So we're debating whether. Yeah, I'm going to stop here because 35 minutes of me rambling by myself typically translates to 50 minutes in the lecture hall. Yeah, and then I can cover all of this when you are in class tomorrow. That makes sense. All right, so